You have fallen into Event Horizon with John Michael Godian.
Ponder for a moment the woolly mice. Yes, actual lab-grown mice with mammoth fur. As if regular mice weren't already testing the limits of human patience. Now we've given them mammoth fur, and possibly an attitude. Especially if someone decides to modify them further and make them the size of mammoths. Well, now I have something else for you to ponder. It turns out we might not be that far off from putting data centers in space. A recent article in The Economist explores how a startup called StarCloud is planning to build data centers in orbit. The idea is that as launch costs decrease, it becomes feasible to place data centers in space, where they can benefit from constant solar energy and naturally cool environments, potentially reducing the environmental impact of our ever-expanding digital infrastructure. This article isn't just a news item, it's a deep dive into the intersection of innovation and space technology. And this is what The Economist does so well. They go beyond breaking news to provide insight and analysis for the things that actually matter. That's why I'm happy to share today's video brought to you by our advertising sponsor, The Economist. The Economist is a globally trusted source of intelligent, incisive journalism with a worldwide network of reporters who cover the most important stories shaping our world. Whether it's science, business, AI, or space, their reporting helps build confidence, making you feel smarter, more informed. If you're someone who loves going beyond the headlines to truly understand the issues facing our world and their implications for tomorrow, and as a listener of mine, I'd wager you are, then The Economist is a must-have in your daily news diet. As a listener of Event Horizon, you can get 20% off your first-year subscription to The Economist. Just go to www.economist.com/eventhorizon to get started.
Joining John today are Dr. Lewis Welbanks and Dr. Matt Nixon to discuss their newly submitted paper with an update on K2-18b. Lewis Welbanks is an astrophysicist and NASA Hubble Fellow at Arizona State University. His research focuses on the atmospheres of exoplanets, aiming to uncover the chemical fingerprints that reveal the formation and evolution of distant worlds. He has contributed to major studies of exoplanetary atmospheres using data from Hubble, JWST, and other observatories. Matthew Nixon is a planetary scientist and astrophysicist specializing in the study of planetary atmospheres and the origins of complex molecules in space. He is currently a NASA postdoctoral program fellow at NASA's Goddard Space Flight Center. His research explores the atmospheric chemistry of exoplanets, brown dwarfs, and solar system worlds.
Luis Welbanks and Matt Nixon, welcome to the program.
Thank you very much for having us.
Thank you.
Now, gentlemen, in your paper, you highlight something very important. This whole thing about characterizing exoplanet atmospheres is something we are just now able to do. This was almost a dream or a very rare fortuitous thing before the launch of the James Webb Space Telescope. And looking for atmospheric gases like this is a nascent field. In other words, it is not mature yet. What makes it that way? In other words, we charge in, we start seeing gases, K2-18b being a fine example, but not just because of the DMS and DMDS claim detection, but also things like methane detections there, and water vapor there, and clouds, even inferred clouds. Are we taking a step too far, going too far without examining our methodology on how we're going to do this, specifically in regards to comparing models and Bayesian methodology?
Yeah, so I can start, I guess. I think that it's been an incredibly exciting time to be working in exoplanet atmospheres the last few years, especially with JWST now. We're suddenly able to see so much in so many planets that we just had no access to before, as you mentioned. And even before we get to planets like K2-18b, these sub-Neptunes or these terrestrial planets, just looking at what JWST is doing for giant planet atmospheres. I mean, before we were limited to these HST spectra, it was very difficult to draw any really robust conclusions about the atmosphere. And suddenly we can see these incredible features of carbon dioxide, of methane, of water vapor, and actually really constrain the compositions of these objects. And it's such an exciting time. But of course, the natural thing to do is to push towards, well, what's the hardest thing? What's the most tricky thing that we can observe? And for JWST, that's going to be these small planets. So these terrestrial planets, do they have atmospheres? These sub-Neptunes, what's going on? What are the detailed gases? But we have to remember that once we push ourselves to the limits of that signal to noise, then we're going to be back in that era like we were with HST and the giant planets, where it's tricky to make an inference where there's no other alternative hypothesis and no other model that could also explain the observations. So I think that's where we need to be really cautious as we get into the limits of what JWST can do.
Yeah, and I think it's nuanced conversation about it's exciting because it's like for the first time in humankind, we're finally at a point where we can actually learn so much about these planets that are outside of the solar system, almost to a degree that it is way beyond what we can do for our own solar system. So it's really learning so much more about things that we have never seen and trying to understand where are the limitations. Like, are the limitations in the models or are the limitations in the data? In a way, it's like we have a new toy and we're learning how to play with it and we're learning how it comes together. It's about learning to place a context of what we know and what we do not know.
Now, when everybody's looking at exoplanet atmospheres, they have to make a comparison. There has to be some kind of a control, which in this case, I believe are just models. You know, you say, well, this, if this is this, it should look like this model, and that sort of thinking. That strikes me as open to flaws. Could you elaborate on your questions regarding that?
Yeah, I think it's just a standard of the scientific method. We have a hypothesis, we have a theory, we have a model for how the world should work, or the thing that we want to test should work. And we say, well, if my hypothesis is right, I expect my observable to be in a specific way. And then I update my hypothesis, I update how I think this particular phenomenon works based on the interactions that I get with the observation. So in the case of exoplanets, it's very fun because, I mean, if we think about what happened in the 90s and thinking about detecting planets, we had the template of the solar system. And what happens when we find the first exoplanet? It's nothing like what we have in the solar system. It's a Jupiter-sized planet that is super close to its host star. It doesn't match our preconceived notions. So when we now are trying to understand the atmospheres, it's like, well, should we have a very strict template of what our hypothesis should be and say, oh, all atmospheres must definitely 100% absolutely look like the things that we know are in the solar system? Or are we allowing some wiggle room? And that is where our hypothesis, our theories get confronted with our observations. And we just need to be updating our expectations and how we're building these models.
Now, does this affect all detections of all atmospheric gases in exoplanets? In other words, with studies that are finding methane around, does this affect that as well? And is there such a thing as a strong enough signal that it sort of moves past this question? Or is it we're just trying to tease things out of the noise? But is there one that's just screaming that passes this filter?
Yeah, that's a really great question. And as I mentioned at the beginning, right, with the sort of larger planets, and even often with the sub-Neptunes, depending on what species you're looking for, I think we can achieve a standard of confidence where I think most people within the field kind of commonly accept that yes, like we've tested this against multiple competing hypotheses, and we've tested it against multiple independent teams have analyzed this data and come to the same conclusions. I think we can safely say that the signal is very large and we can uniquely attribute it to something. So, for example, I don't think that anyone is really debating that there's methane in the atmosphere of K2-18b at this point. A number of teams have performed the analysis and they all find very high confidence detections. And they've compared, a range of different models, and it seems to really hold up under a lot of scrutiny. So I think there's a lot that we can say for sure about these atmospheres going forward, but I think it's just tricky whenever we start to look at the more exotic ideas. And of course, they're really exciting and we want to test them. But if we're going to look for these more exotic species in these atmospheres, we also need to work our way up from the basic things that we expect to be there to the maybe slightly more unusual things, and test each thing on the way and rule it out before we get to a more complex molecule. So I think that's where it becomes hard to make a strong detection.
From my perspective, I think it's not a challenge that is unique to exoplanet atmospheres. It's a challenge to the human experience. Like, how do you know that you know something? How do you know anything with full certainty? How do we describe what a detection is? So, given that we are inheriting aspects from spectroscopy, from astronomy, and now we're also getting into the aspects of life and geology, we are really recalibrating our rulers. And in a way, we are trying to build a quantification, a framework where we can actually statistically tell you what certainty is, because science perhaps is not about trust and faith. It's about telling you, well, to the best of my abilities and to the best of the tools and the knowledge that I have, this is what I'm certain about. So we're trying to build some scaffolding, perhaps, to say what is the detection. So off the top of my head, some of the things that have been proposed is, well, for you to know that you actually detected something, first you want to make sure that there is a signal, that in your spectrum that you're getting from the planet, there is a bump. And that no matter who reduced the data, no matter what telescope observed it, or any of those circumstances, there is indeed a bump. So fine, that's the first check. Then the second check is, what is the origin of that bump? Is a bump perhaps something that happened at the telescope level? Is a bump something that happened in the star, actually, and we're seeing something that was star produced? Or is it indeed atmospheric? And that aspect is a little bit of the attribution. So just because you have a signal in your spectrum, can you uniquely identify it as a specific component? And then once you know for sure that it is that component that is astrophysical, that it belongs to the planet, and it is a chemical species, can you then talk about the attribution? Like, what is the chemical process? What is the condition of the planet that gave origin to that particular chemical species? So currently, I think we are pushing towards this third step for many of these planets. So for the hot Jupiters, off the top of my head comes the early release science observations of JWST. Like, there was for sure a big bump, and no matter who reduced the data, the bump was there. And then the bump was CO2. And I was like, well, could it be something else? Like, do we have incomplete line opacities and do we have incomplete sources? Well, if it's CO2, we should be able to observe it at a different wavelength. So then there's a little bit of prediction and boom, it's there. And then we can start talking about, well, what should be the physical and chemical composition of the planet that gives origin to that amount of CO2? And even then, we're still having some challenges and there's some uncertainties, but I'm talking about how metal enriched the planet is within like a couple decks. Like, it's 10 plus or minus 5. It's okay. So we're now getting to that level. So yes, we can say definitely things about detections. But see, even in that level, I didn't talk about statistics. I just like, oh, I have these different checks that as a scientist I can hold in, as part of my thinking and my rationale and going through alternative hypotheses.
Now, how hard is it when you're characterizing an exoplanet atmosphere like this? How hard is it to tease that out from the star itself that it's transiting? And that what do you have to do with the star itself before you even see the transit? Do you have to just deeply characterize the spectrum of the star so that you know what to expect? And then you look for the difference during the transit. So how hard is that? How involved? What's the step-by-step process of cold looking at a star and then being able to, it has an exoplanet, it's transiting to that stage to where you can even characterize it? What do you have to do to lay the framework with the star itself before you even look for these spectra?
Yeah, it's a big question. I can start, and Louis, and there's so many different aspects to this, and it's a really big problem in the field. Is like, how do we make sure that we're modeling the star correctly and then removing any stellar imprints onto the signals from the planets that we're seeing. And I think from the end that we work in terms of modeling these data sets, we're always interested in, okay, well, we can see these decreases in stellar brightness caused by planets, but they could also be caused by things like star spots. So that's something we try to understand and try and fit for and try and model for when we, first of all, create the transit light curve. You can actually see the effects of if the planet crosses a star spot, and you can fit for that. You can detrend your data accordingly. But then also if there are unocculted star spots, that can also impact the spectrum. And we know some of the signatures of those kinds of effects, and we can include them in our hypothesis space. So we allow for different spots or bright faculae on the stars, include that in our model parameter space that we explore, and then we can test in a comparative way. Well, does a model where there's just star spots and no atmospheric signals outperform one where we enable atmospheric signals? So from a perspective of modeling, those are the kinds of ways that we account for it. But it's still in many ways an open problem, and there's still ways that we can improve our stellar modeling and also gather more observations of the stars. And this is something that a lot of people are putting a lot of time into, especially as we look around these smaller stars, so these M dwarf stars that a lot of our small targets, our small planet targets, are orbiting. Because in some ways they're much easier to characterize because the star is smaller, and so more of the light gets blocked out as a proportion of the area of the disk of the star. So you get a nicer signal to noise ratio, but also these stars are actually the most active and often have the most issues with star spots. So there's kind of, there's pros and cons of doing this kind of observation, but lots of challenges.
And the fact that there's no boring day at this job, that what we thought was true yesterday, it's probably not true today. It's definitely not going to be true tomorrow, because in the Hubble years, we're like, it's fine, stellar activity, we don't have to worry about it. And there were some trailblazers that are like, no, actually, you have to worry about it and you have to know thy star. That's one of the main things that we've been seeing from JWST. It's like, wow, you actually have to worry about the star. And not only that, the star that you are observing today, for all intents and purposes, it's going to be absolutely different from the one that you observe in a month. So can you really match the observations? Is the astrophysical environment that you saw a year ago when your first set of observations taken, can you really combine them? And that is just a star. So imagine when we figure out all these kinks and then we realize that not only the star is happening and it's angry and whatnot, also the planet is variable. Like if we get to that point, and it's largely driven by the quality of our observations. So JWST is finally giving us the precision to push the boundaries of what we can observe.
Yeah, and I really expect that in the near term, we're going to learn so much more about stars, almost as a byproduct of what we're trying to learn about planets. So that's another really exciting outcome of JWST, I think.
Yeah, and I have to admit that one of my fascinations starting as an amateur astronomer was stars, obviously. And I maintain that is that the stars interest me. And I remember specifically like with the Kepler mission, everybody's looking for transits, dips and everything. I'm sitting there looking at the flares coming off of the stars that you could see in the light curves. So I'm hoping for more characterization of stellar physics from JWST. But I think we're getting that. But that's going to play very deeply, as we were talking, that's going to play very deeply into characterizing exoplanet atmospheres, because I don't know that we know the ground rules yet, which is what you're saying in your paper, essentially. Now, with a planetary atmosphere, now K2-18b specifically has a water vapor detection. But that water vapor detection, as I recall, was a little bit weird in that it was changing, as you mentioned, that sometimes these change. And this one was, and they inferred clouds. How do you know that's what that is without a long observing session, lots of data? Or if it was just a fluke, you saw something, something glitched, and it wasn't a cloud, it was just a glitch. How do you tell the difference between some statistical anomaly or whatever versus a cloud?
Yeah, I guess it's kind of two parts, right? There's the water detection and also the cloudiness of this planet. And when it comes to the water detection, I think that's a really good example of what we were talking about, where JWST has really transformed our understanding of these objects. So that initial water vapor detection came from observations with the Hubble Space Telescope. And one of the challenges there was that the wavelength coverage of Hubble was reasonably limited to just kind of one strong absorption band that would correspond to your water vapor. But unfortunately, another chemical species, methane, also has a very strong absorption band at similar wavelengths. And by looking at the HST data and doing our best to model it, we did conclude that it looked like at the time that water vapor was the better fit to the data. Whenever you try to model with water versus methane, the water seemed to outperform it. But because you're only fitting to that one band, it was really hard to say anything particularly conclusive. And then JWST came along, and where it's really strong because it has this broader wavelength coverage, is you can start to get multiple absorption bands. And that's something that really helps you uniquely identify a particular chemical species. And when we got those additional bands, we actually realized that what we'd been looking at all along wasn't water vapor absorption, it was in fact methane. So that's just an example of how, even if your models prefer one hypothesis to some extent from an initial set of observations, you've got to try and follow it up or try and get some complementary observation, additional wavelength coverage to really figure out if what you're seeing is really true or if it's something else going on.
There is this cool layer to the story of HST, right? With JWST, the observations that strongly favor the presence of methane over water, they're effectively a single shot. They took the spectrum in one visit. The Hubble observations, if I remember correctly, were 9 orbits of Hubble. And again, just like a couple minutes ago, we're talking about how perhaps the star that you observe today is not the one that you observe tomorrow. So out of those 9 transits, one was corrupted because some issues with the guiding or something happened with the telescope. So then they were able to use 8. And then they used the 8 orbits to build the spectrum that you get to observe, and that was used to do the inference of water. But we could play the game and ask ourselves, like, well, what happens if you use 7? Or what happens if we had actually used the 9th? And could there be actually a signature of methane in those HST observations? But it depends on how we went about our data reduction, and questions about how is that particular spectrum built? Like, where are the bins and how are we sampling that feature, especially, like Matt was saying, when water and methane are very degenerate, like they overlap significantly at that particular wavelength range. So right now, what we say is that Hubble found water and JWST didn't find water, but found methane. I'm curious, hopefully, I don't know, in a couple years or whenever, we may resolve that, and maybe there was no significant tension. Maybe there is water and methane. And it's just about how do we put the pieces of the puzzle together to get a holistic picture of the planet.
You know what intrigues me about that specifically is, okay, if you have a methane, you've got methane there, and to even see it, you have to have a lot of it. And with K2-18b, as I recall, it's like 1% of the atmosphere. How is that methane surviving so close, orbiting a red dwarf? You would think it would get disassociated quickly. So there must be a source creating a lot of methane there, whatever it is. Any ideas on that?
It's a fun of chemistry and trying to think about what these planets will be and what their composition may be. So yes, one of the things is that if there is methane, like you're saying, photochemical reactions can happen and methane will be destroyed. So it'll be interesting to think, well, what photochemical products may happen after the destruction of methane. But also it's about thinking of what are the equilibrium states of different elements. And if you have a ball of gas at a given temperature, how those different elements recombine. And at that temperature range, we actually expect that methane will be one of the dominant sources of opacity. We expect a significant amount of methane over CO2 or CO.
Yeah. I think also, I mean, this has been something that JWST has revealed to us just very recently for these sub-Neptune planets where we know they have to have some kind of substantial atmosphere. A lot of the leading theories pre-JWST were that these were probably mostly hydrogen with only trace amounts of other chemical species. And actually we're observing, K2-18b is a good example, but there are other sub-Neptunes where we see really substantial amounts of other heavier chemical species. So methane, CO2, water vapor, at amounts that were probably much larger than a lot of people would have thought. And so it's now a really active area of research as to like what are the processes that can produce such an atmosphere. And some of that could be that there's atmospheric loss going on that preferentially removes hydrogen from the atmosphere versus heavier things. And also potentially these spheres could be in contact with like a molten magma ocean that's violently interacting with this hydrogen, producing all these different products that we're then potentially able to see in the upper atmosphere. But we're still working on figuring out exactly how that interaction deep in the interior of the planet would actually propagate into the part of the atmosphere that we're looking at. So this has really sparked this huge area of research that I think a lot of people are really excited about.
Yeah, finding a giant magma ocean planet that's eight Earth masses is going to be, that would be as interesting as a microbe, almost. Not quite, but almost. And that goes to show you how alien these things are. And to hammer the point home, we do not have a Mini-Neptune in this star system. And this is a completely new class of planet that nobody knew existed until we saw one not that long ago. So how do you know what they do? How do you know what those planets act like? And that's the problem that I see here, is that we don't know. And we may see that alien worlds are far more alien than we thought. And as you noted, Now, with K2-18b, there is also the detection of a much, much stranger gas, dimethyl sulfide or potentially dimethyl disulfide. And these are linked with life, but maybe not. And there has been some work done saying, well, it was detected in a comet, which is obviously abiotic somehow. Or there was also the detection from the 1980 paper that you guys sent me that yeah, maybe there's another path, a chemical path that doesn't involve life. What are your views on that? I mean, to see that gas and say that this holds up, say that the detection holds up, and it's there, what could cause that abiotically in that great of a concentration for us to even see it? Because I don't know that we would see Earth in this regard from a distance, because there's not a lot of this gas, but it is present. So any ideas on a process that can happen in a mini-Neptune atmosphere that can produce this?
Yeah, so I think one thing that people have recently started looking into, and I think that some of this has been sparked by the discussion over DMS that's been really interesting to come out of this, is people have really started to look into these different sources producing these kinds of exotic molecules. Can you do it abiotically? Are there other ways? And it's still something that there's work to be done to understand this, but I think one of the interesting angles that people have been looking at is essentially photochemistry, right? Where photons from the host star interact with things like methane or like hydrogen or H2S, nitrogen in the atmosphere. And these hazes that form as a result of that can then lead to the production of these more exotic molecules. And I think there's been a recent study that suggests that you can see quite a lot of DMS just from that. No, I think there's still more work to say, well, is it going to be substantial amount? How much would we see? And then maybe we could formulate a hypothesis as to saying this is the kind of amount of DMS we might expect to see if we're able to see it all. And then we can go out and try and test that observationally.
And I think that both are not at odds with each other, right? I go back to the whole idea of, is the bump there? Can you attribute it? And can you know exactly what is there? So yeah, maybe the feature is there. Maybe indeed it's DMS. And then there may be N processes that will produce DMS. And we will have to engage in a rigorous and honest conversation about, well, why one may happen and the other one may not happen. If we've learned anything from exoplanets in the last 30 years, is that our imagination plays tricks on us because we are more willing to go for the exciting thing and be like, oh, of course it's this, rather than just thinking, oh, well, why shouldn't we just rule out our solar system? But also that our expectations are subversed. With the big planets where we have big features, we do engage in serious conversations about how there's iron raining on the one side of the planet, where there's clouds made out of diamonds or rubies. Like, well, if that can happen, I'm like, well, maybe there's a process where under extreme circumstances, carbon, hydrogen, and sulfur do get mixed in a way that ends up giving you DMS.
I think what sticks in my mind is whenever you see sulfur, you start to think, well, volcanoes, and the magma ocean comes back.
Yeah.
And that what's the chemistry of, again, as you mentioned, a very vigorous interaction between a global magma ocean and its atmosphere. What's that like? Well, we don't have one of those in the solar system. So who knows what the chemistry is? And the other thing is that, I mean, that's a different star. That is not the sun. That's a red dwarf. And again, you talk about photochemistry. Well, what's the profile of that? Because you've got ultraviolet coming off that thing, things that our sun isn't quite doing. So even the star itself is a member of its own star system, and it too is going to impose some rules, right?
And it's very exciting that you say that, because as we were doing some of the photochemical models, it's sobering to then realize, oh, I want to do the absolute best job that I can, but I don't have a good UV proxy for the star. Like, I don't have a good stellar spectrum for K2-18, the star. So maybe that's something that we should be doing. Like, it reminds me of what you were asking earlier about, like, well, how much do we know of the star? There is a significant need for having simultaneous observations and follow-ups. Like, wouldn't it be amazing if we were able, or we had the chance to look at K2-18, the star, simultaneously, like consistently for a month before the transit, and then during the transit and after the transit? If we knew exactly how the star was behaving, to just get estimate of what sort of UV spectrum it had and how maybe we can model these photochemical reactions. That is what I think is really a golden opportunity to push our knowledge.
Another thing that's often talked about in astrobiology is the idea that red dwarfs strip atmospheres. And what is it that this Mini-Neptune has? Is it just simply gravity that allows it to even hold on to an atmosphere at all? Or could we be completely mistaking everything and that this has no atmosphere and that we're seeing a trick?
Yeah, so one of the nice things about K2-18b is that we can be pretty certain that it has retained an atmosphere thanks to just its bulk density, right? I mean, this thing has a puffy enough radius that it just can't be explained by being a giant ball of rock. So we're in a regime where it must have held on to some kind of atmosphere, and yeah, basically, I think there's a process by which once you get enough gas, you're going to be resistant to that kind of loss. So when we look at these kind of different populations of the Mini-Neptunes and super Earths, and we have all these different names for them, and the ones on the smaller end are typically planets where, yeah, that atmosphere has been stripped entirely, but some of the lucky survivors that maybe get a little bit less irradiation are able to hang on to those atmospheres for a long time. And we can tell that just by even before going and doing atmospheric spectroscopy, we can get a good sense of whether a planet is likely to have an atmosphere or not, just from its mass and radius.
And one of the things that I am very excited about JWST finally giving us the opportunity to do, and Matt and I both are involved in this program, it's the idea of observing the progenitors of the Neptunes that we see today and the super, because we, as you're saying, we don't know how these planets retain atmospheres or they don't. So hypothetically speaking, let's imagine that there is a family of baby planets and we can observe them as they get irradiated. And then we see, well, maybe some are able to retain their atmospheres, some do not. And maybe we can actually start mapping this taxonomy of planets, but rather than just focusing on the mature planets, we can see them as a function of time and really understand these paths and say, oh, well, maybe K2-18b comes from this particular family of systems that, for reasons that we still don't know, but we're trying to understand, they were able to keep their atmospheres. They were not exposed to these environments and they held onto their atmospheres. But this other group that now we see as bare rocks were not able to hold onto their atmospheres. So that is a very active area of research for the community of really trying to chart where this, let's call it the cosmic shoreline, where these planets are able to keep their atmospheres or not keep their atmospheres. But obviously that's a function of many things, one of those being the type of star.
Now, is it useful to look at young star systems? I know K2-18b isn't all that young, 2-point-something billion years old, so it's a relatively mature star system. But in the case of a recent star system, a recently formed one, where the rocky planets in them that are close to the red dwarf might still have their atmosphere, but it's actively being stripped. Is it fruitful to look in that direction? Because I know we've seen some evaporating planets that are doing this, but specifically, if you want to look at Earth-like planets, that might be the thing to do if you can see them at all, which, that's always the big trick, isn't it? But if you can see them and you can see them losing their atmospheres in the act, wouldn't that enlighten us greatly?
Isn't it great that you're asking that?
Yes, absolutely. Yeah, no, absolutely. I mean, this is exactly something that Luis and I are working on actually using JWST to observe some of these young sub-Neptune progenitor planets, or things that we think are sub-Neptune progenitor planets. So yeah, within the first few million years, few tens of millions of years of their lifetime, and that's what we're really hoping to see. We're hoping to see signs of like these things having these puffy atmospheres and maybe being able to tell how quickly they're losing those atmospheres, whether they're likely to evolve into things that, end up just becoming bare rocky planets, or whether they end up becoming sub-Neptunes, things like K2-18b. And yeah, I think really getting that understanding of what's going on at the early times will really, really help us. And the same thing with this idea of these global magma oceans. If we can find a planet like this, there's also the question of, well, how long can it hold on to that kind of magma ocean? How long does that process take? And how much can it change the atmosphere composition? So if we can have something old where we know the final atmosphere state, and we can find something similar that's really young and know the initial atmosphere state, then we can actually finally pull all these pieces together and start to say something about what the processes are that are going on.
I think it'd be interesting to study a star system, if you could find one, where it's still in a period of planetary migration. We know the solar system had quite a great period of migration, and how that affects atmospheres. In other words, You lose some when you're close, but if you're further out, you retain some, and you might end up with these fossil atmospheres that give you a clue as to what the migration in that star system was like. Am I off base with that? Is that something that could be done if we can find a actively migrating young system?
Yeah, we're also part of this program where we're going to be observing a system that we know it has a transiting planet, but also has its remnant disk, so it's still dissipating the disk. So this is it's I think it's one of the few, if not the only one, that we can actually catch this process of migration and these things that we're trying to put together with mature planets, but catch them in the act and say, oh, okay, so that's where the disk is, and that's how the planet is behaving today. So that is a unique anchor point as a function of time.
Now, any hope with JWST? Now, we're looking at red dwarfs because they're easy. Not a lot of glare compared to orange dwarfs and yellow dwarfs, or whatever you want to class the sun, green giant, whatever you want to class it. Now, in the case of true sun analogs, can we do anything yet with characterizing planetary atmospheres around those? I know we can kind of look at them and see wobbles and things like that, but is the glare factor just too great to do this kind of work with a star that's like the sun, and we just aren't going to be able to tease out these spectra from that because of the glare? And is there any hope to build a telescope that can mask that?
Yeah, so I mean, in terms of what we can do with JWST, and I think in the future this is something we'll be able to do even better. I think the way to think about it is like the contrast between the planet and the star, or the difference in size between the planet and the star. So if you have a smaller star, then you'll be able to get more of a signal from a smaller planet passing in front of it. If you have a larger star, you can still get a pretty good signal if you have a larger planet. So with JWST, certainly around even these F, G, and K, these sun-like stars, we have been able to characterize the atmospheres of giant planets, and even pushing down sometimes into the sub-Neptune regime. If you get a really good target that's just right, you can observe it, and maybe you need to get a few transits to build up that extra signal, but we can definitely do it, and we already have some examples with JWST where we've characterized even sub-Neptune planets around F, G, and K type stars. I think for the rocky planets, we're really focusing on the M dwarfs now because that's what's most achievable. But yeah, I mean, I really hope that before long there'll be another telescope coming along that will help us do the Earth-like planets around the sun-like stars.
Yeah, I think we want to have bigger buckets of light. We want to have the opportunity to have as big of a telescope to collect the most information. And I think the extremely large telescopes, the ELT in Europe is going to be fantastic. And whatever direction the other telescopes go, it's just getting that is going to be helpful. And also being able to discern the specific spectroscopic lines. I think that is the other key advantage that we may be able to pull off is that, sure, the star can be very different, but if we have a big enough telescope and we're able to resolve the Doppler shift between the star and the planet, and we are able to look at the atmosphere in high resolution, then we can talk about not talking like detecting broadband features of a particular absorber, but actually getting the resolved lines and the specific transitions of different molecules. I think that is a type of facility that will be able to help us.
Now, the one thing about K2-18b, the elephant in the room, is the possibility that it might be a Hycean world, an ocean world. And we've never seen one of those. It's just hypothesized that such a thing could exist. Do you think that there is an indicator or is not an indicator that this might not actually be a Mini-Neptune, but instead the hypothesized Hycean world?
Yeah, I think that the Hycean world kind of theory was spawned by K2-18b, and this was a number of years ago when we were looking at the interior structure of this planet, and we find that there was a really wide range of different interior structures that were consistent with what we knew about the planet at that time, which was still reasonably limited observation. We had our Hubble observations, and we knew the planet's mass and radius. And at that point, there was such a wide range of possibilities still open, and some of those did allow for the idea that liquid water could be at the surface of this planet. And once again, that's something that sparked a lot of additional modeling work. And I think that there are some more climate studies that suggest it's pretty hard for K2-18b to retain that liquid water ocean. But I think really the task we want to do is to look at what actually could an atmosphere interacting with an ocean produce, and how would that be different from what we would see if it was in fact, say a gaseous planet interacting with a magma ocean. And there are some ideas about what chemical species we would expect to see or perhaps not see But again, this is the sort of thing we were talking about before is, first of all, we want to be able to identify certain gases, and then we want to be able to attribute them to certain effects. And so we're at the point still we're trying to distinguish between these different ideas. I don't think we have the really obvious candidate thing that would confirm for us 100% that there is an ocean or there isn't an ocean. So I think there's still more work to be done there.
As an idea, I like it. I think that it is exciting to think that, again, conditions outside of the solar system are very different from what we would expect. And whether K2-18b is a Hycean world, I think there needs to be more information and more validation to indeed go from detecting a feature to attributing to the gas to determining now, which we are getting to do that, to go from the atmosphere to the interior of the planet. That is actually now a possibility, and we're getting to do that. And I think one of the challenges is that it may be worth being clear in what we mean when we throw around these words. Like, for example, given that we don't have a mini-Neptune in our solar system, what do we mean by a mini-Neptune? And how much hydrogen does it have to be called a mini-Neptune? My favorite example is also to think about the rocky planets. Well, Venus is a rocky planet, Earth is a rocky planet, Mars is a rocky planet, but they are very different. So yeah, maybe the mini-Neptunes do have different flavors and come in different shapes and forms, and they may exist. But saying, oh, this planet for sure is a Hycean world because I don't see something or I see something, that is a complicated argument that becomes difficult to falsify and difficult to verify. So without that, the scientific argument kind of falls flat from my perspective.
Now, how do we improve in the near term over the next however many years JWST has left? How do we improve the methods? In other words, do you just build a bunch more models, build as many as you can for comparison purposes with your observations? Is that the solution here for that aspect of this problem?
So I think that part of the solution is definitely to make sure whenever you have a new data set and you want to try and interpret it, that you look through all of the plausible hypotheses that you can think of to explain the spectrum and try various different things and see what you can and can't rule out. And you should start, I think a good idea is to start from something very simple, something that just takes what little information we have already and produce a simple model and see, is that sufficient to explain what we're seeing, or do we need to invoke something more complex? And then we can kind of build up the ladder from there. So if we see a bump that doesn't quite correspond, if it's very, very high significance, then we can start to think about, well, okay, what else might be able to explain that? And we do have a lot of modeling at our disposal at this point that can help us determine these kinds of, say, photochemical products and plausible things that could be in these atmospheres. So I think it's really important when we're interpreting the observations to look at what's been done already and to take into account all the different possibilities that have been put forward, because we have a lot of modeling tools and there's still a long way to go. But I think just making sure that we're very systematic in ruling out alternative hypotheses before we come to a strong conclusion about what's going on in a particular atmosphere.
For me, it's about moving forward. It's about context. It's about knowing our limitations and not being afraid about it. I think that is how knowledge is created, and knowing that we are limited and we're doing the best that we can with our existing framework. We will fall for some traps, but they will not be traps as long as we say what is happening. I always think back of like, well, when I talk to my family, when I talk to my friends, what is the thing that would absolutely convince them that I made a breakthrough discovery? What is the irrefutable proof that they would be like, oh, yes, this is definitely the thing that is going to happen. So being able to translate our detections and our results from a preference for one explanation over another to a certainty, that requires going through the nuances. And the way that I say that, and it's cliche, but in other fields I've said it, is imagine that we're trying to explain the composition of the moon, and we only have a cheese model and a sponge model. If those are the only two models that we have to explain it, well, one of the two of them is going to win, and maybe the cheese model is going to be preferred at 6 sigma, and then I'm going to go and say, I found cheese at 6 sigma. And yeah, it's true, I found cheese at 6 sigma compared to sponge, but that doesn't mean that we found the true answer. So engaging in that exercise is still fruitful, so long as I tell everyone, yeah, relative to this model, and this is how we're going to improve. And these are my unknowns. Let's work together to push the field forward.
I think also, it is easy for for that stuff to get lost in translation or lost in the excitement. But I think there's still so much that we can say about these planets already that's really exciting, that doesn't need hyperbole and doesn't need, and the things that we've been talking about, these lava planets, these magma oceans, these iron ray, and there's so many crazy things going on that we can observe in really great detail, that I think we should make sure that we're looking at things, we're looking for what we can see, and making sure we're going through all these crazy possibilities and not crazy possibilities, and figure out, because we will find exciting stuff. We will find exciting stuff for sure. There's so much excitement out there, but we want to make sure that when we find the exciting stuff, that it's, we're sure that it's what we're seeing.
It started exciting. I remember when we had no confirmed exoplanets. In the 1990s, the early 90s, we still hadn't found one. Everybody knew they must be out there, but it hadn't confirmed. But the first ones we found were they're around a pulsar. These dead bombarded worlds around a pulsar, and that's, as I recall, those were the first ones that were confirmed. Fascinating field, gentlemen. Thank you for joining us today, and I look forward to continuing to constrain this down so that we actually know what we're looking at with the JWST, the power of that telescope. It's better than we thought it was going to be.
A really fun time. Thank you so much for having us.
Thank you so much.